Hello Matrix, welcome to another video, and today we're going to be looking at the memorandum from the Free State from your term 1 exams for this year. Alright, this serves as a practice or a revision for those who wrote this paper, and it serves as a guide as to how much you should be working if you are writing the major exams as the upgrade. And also it helps one to prepare for the June exams for the matriculants of this year. Alright, so let's not waste too much time and just jump into it without wasting time. Okay, I cannot overemphasize instructions. Important is to notice that you are given a data sheet. You are to consult it if you need it, but you're not forced to use it. And then the next one is to show all formulae, substitutions in all calculations, because this is where you score marks. And then this one, the rounding off of numerical answers, is to a minimum of 2 decimal places. This means 2 or more. And then here you can give a brief motivation, a discussion, etc. where required. Okay, so let's move on. Now, question 1, you know it's MCQs, and you can read the instruction. It's pretty standard. 1.1 says a suitcase is at rest on a table. Okay, it is at rest on a table. Which one of the following is the reaction force to the weight of the suitcase as described by Newton's third law? Okay, so what is going on in here? Well, we know that we have a table. Okay, and then there are its little thing is there, and that's the ground. And then we've got our suitcase here, okay, with the handle and stuff. Now what do we know? We know that the earth is pulling the suitcase down, and then it gives us its FG, right? Right. But the problem is now this suitcase being pulled by the earth in terms of its weight, this suitcase should be pulling the earth, isn't it? But the problem is that the earth is not pulling the suitcase alone. There is an interface, so it means its force will be transmitted through the table, meaning the earth for me is going to be pulling these two as a unit. Okay, so the earth is going to be pulling these two as a unit, because it's impossible for the earth to pull this suitcase alone, because look at it, what is in between the earth and the suitcase? It is the table. So whatever force the earth is going to be applying onto the suitcase, it is transmitted through the weight of the table. So questions like this for me are not the best. In fact, they are ridiculous. I don't know why they even feel the edge of trying to trick students by asking these lousy questions. It's honestly a lousy question without sounding, condescending or anything. For me, it's unnecessary. It's not even. I mean, they asked this question in May, June last year. It's terrible. I know they are going to propose this one as the answer and says the force of the suitcase on the earth, which for me, I have a problem, because the force that is reacting here, it's going to be that of the earth on the unit of the table and the suitcase. So for me, this scenario is all wrong. So I will not answer this one. You answer it yourselves. Of course, they are most likely are going to propose B as the answer, but I have a problem with this kind of a scenario. So for me, it doesn't come out nicely. So I just forget about it. Okay, let's move on. 1.2, a horizontal force F is applied to a crate, causing it to move over a rough horizontal surface as shown below. Okay, if this surface is rough, it means we're going to have frictional force. But since this is movement, it's going to be kinetic friction. What other forces must we think about? We can think about the weight of the crate. And what other force must we think about? The normal force. Okay? But because this object is neither dipping into the ground nor being lifted off the ground, it means these two are balanced. Okay? Great. So the only forces that are responsible for the movement is the applied force and the kinetic friction, which are opposing each other. So now I asked a question here. The kinetic frictional force between the crate and the surface on which it is moving depends on. So first of all, we know that kinetic frictional force is given by mu k, which is the coefficient of kinetic friction multiplied by n. So we know that this is the normal force. Normal force in this case is balanced by the gravitational force, so it depends on the weight or the normal force. So it is not necessarily anything else. Is it the applied force? No. It has nothing to do with the magnitude of frictional force. How fast the crate is moving is not responsible for that. The upward force exerted by the surface on the crate, that is definitely the normal force. So what we're talking about there is the normal force. Okay? So is that true? Yes, it is true. And then the surface area, not necessarily. So the answer is C. Okay? Great. Now we're told here, object P exerts a gravitational force F, okay, on object Q. When the distance between them is r. So basically we know that this force F is given by G MP MQ over r squared. Okay, that is the story that we are being told. Now we're told the distance r is doubled. So this means we've got ourselves this force that we don't know, okay, which we're going to say is going to be G MP MQ over, then this is 2r, and then we square that. This gives us a quarter, okay, because this is going to be 4r squared. So when we factor out that fraction, we remain with GMP MQ over r squared. This is the same as a quarter of f, because we know that this expression represents f, okay, in the first scenario. So the answer becomes A. Okay, so these are some of the questions you need to work out the answer. You cannot just sniff it in the air. But this one is much simpler, because even if you didn't perform the calculation, you could easily work out that it's going to be a quarter of that force. Okay, let's move on. 1.4 says an object of mass m moving at velocity v, okay, mass m moving at the velocity v, collides head-on with an object of mass 2m moving in the opposite direction at velocity v. Okay, so same velocity, different masses. Immediately after the collision, the smaller mass moves at velocity v in the opposite direction. Okay, and the larger mass is brought to rest. Okay, great. Refer to the diagram below. Ignore effects of air friction. So if that is the case, we know that we are creating some sort of a closed system. Okay, so that is something we have to keep in mind. And then we have a diagram there. So it says now which one of the following is correct? Total momentum. Remember, total momentum in a closed system is conserved. Anything that says otherwise, we disregard. Okay? Great. Then total kinetic energy. That's a story for another day. Okay? So these questions can be tricky. In a closed system, we know that total kinetic energy can be conserved, but it is not necessarily always. Okay? It may or it may not, because we know that in a closed system, energy can freely be exchanged. But we only know that the force is acting. There are no external forces. But energy can leave or enter the system. That's why kinetic energy is a bit of a controversial story, whether it is conserved or not conserved. All right. So let's look at it anyway. So if we calculate the total kinetic energy before collision, this is going to be equal to half mv squared plus half of 2m, and then of course this one is in the other direction, so we're going to say minus v squared. What do we get here? This is basically 0.5 mv squared plus this one is going to be 1 mv squared, and then this is 1.5 mv squared. Okay, that is the total kinetic energy before collision. But what happens after collision? I don't know why I'm writing like that. This one is going to be half m into minus v, because it's now in the opposite direction, squared plus half 2m. Now the final velocity is 0. So this is basically 0.5 mv squared. So can you see the kinetic energy after collision is less than the kinetic energy before collision. So it is not conserved. So this is again one of those questions that can take you down. I remember there was a question I've done, I think for the Free State, the MCQs. There was a bit of a situation there regarding this thing. So yep, so these are some of the issues that can come through. But in any case, we always follow the diagram that we are given. At least it makes a lot of sense to choose these two as the answers. Okay, let's move and not waste time. Now a ball is thrown vertically upwards. Which one of the following physical quantities is non-zero value at the instant the ball changes direction? That is at the maximum height. Okay, so we've got our ball here. All right, and then we're projecting it upward, so it's going to go reach the maximum height and then come back to the same position. Okay, so we know that, well, the time it takes to reach the maximum height, which we can say t1, is going to be the time that it takes to reach the same height it was projected from. So we know that t1 is equal to t2. That's time symmetry. Okay, so these are some of the things to think about. But now remember, this is projected upward. So the issue is, if we draw a free body diagram here, we know that there's going to be weight directed down. Okay, I've got indents and length. And then we will see that there's going to be air friction. Actually, this is wrong. Air friction is also going to be directed downward, isn't it? Yes. But because this object is moving upward, it is going to be decelerating. I don't know which one is bigger than the other. This is Fg. This is going to be air friction. Because we were not told anything about air friction here being ignored or anything. So basically this force together they will be decelerating this ball as it is moving upward. So it's going to have an acceleration of some kind, but this acceleration is not g, okay? Because we were not told anything about the system in question. So we know that we're going to have an acceleration definitely directed down because these two forces are acting downward. So this will happen even when it reaches the velocity of 0. It will still be accelerating downward, okay? And then it will accelerate downward. But on this end, it's going to be the weight against F friction. Okay, so these two are now opposing each other. So which already tells you and I that the time this ball will take to come down, in fact, now our statement becomes wrong here. This cannot apply actually, because now the magnitude of acceleration in this instance is not going to be the same as the magnitude of acceleration when it went up. So we know that T1 actually should be greater than, is it greater? No, is going to be less than T2, right? Because this one, there's two forces acting in the same direction, so it will take a shorter time to decelerate to 0. But because here they are unequal, so essentially the magnitude of acceleration here is going to be much less than in the first instance. Therefore, it will take longer time to reach that velocity from which it was projected. Okay, so in any case, what do we understand here is that the acceleration is non-zero here, irrespective of what kind it is. So velocity at the maximum height, when it changes direction, velocity is 0, so it's not correct. Momentum, because we know momentum is the product of what you call mass and velocity, and because velocity is 0 at the maximum height, therefore it is 0. Acceleration is non-zero because we are decelerating even though we're changing direction, and the reason we're changing direction is because of acceleration. But this time we're not talking about g per se. Kinetic energy is half mv squared, and because of velocity is 0 at the time it changes direction, so the kinetic energy decreases to 0, so it is not non-zero. So the answer becomes C. All right, so that's it. It's taking a bit of time, né? Anyway, you always need to think about these things. Now a ball is released from rest, okay, from a certain height above the floor and bounces off the floor a number of times. So we know that the initial velocity is 0 there. The position time graph represents the motion of the ball, of the bouncing ball from the instant it is released from rest. Now this already tells us that this is 0 right at the origin. We're already seeing that in the graph they took the position of release as 0 reference, and essentially they took downward as positive. Okay, always inspect these graphs and make sure you understand what's going on. And then we could see that this reached point A, which is, by the way, ground. Okay, and then it bounced off the ground to some new maximum height B, and then it went to C, which is the ground. Okay, and then it went to a maximum height and then reached whatever that position is. So they didn't show us whether it went to the ground or not. I'm going to leave that alone, but my ground looks terrible. Okay, that's much better. Anyway, now it says when ignoring air resistance. So this means we're creating a closed system. All right, so it says now which point A, B, or C, or D on the graph represents the position time coordinates of the maximum height reached by the ball after the second bounce. Okay, great, because remember this is the first bounce. It bounces up to the maximum height and then it bounces the second time and then it reaches the maximum height D. So the answer here is D. Okay, great stuff. So not a complicated question. Now, which one of the following momentum versus time graphs, we're looking at momentum time graphs, represents the motion of an object that starts from rest? If it starts from rest, the initial velocity 0, moves in a straight line under the influence of a constant net force. So we know that the net force is directly proportional to acceleration. So once the net force is constant, it means there is a constant acceleration, right? Right. And then we know that acceleration in general is the change of velocity over change of time. So if we solve for velocity, we know that it's going to be acceleration times delta t. We can make this one equation 1, okay? That's what we know. So all we know is that, look, velocity is directly proportional to time when acceleration is constant, because we know that our acceleration is going to be essentially constant because the net force is also constant. All right, great. So we expect a velocity time graph that is of this sort. Right, so this is going to be time in seconds, and then this is velocity in meters per second, of course that being the origin. So all of that is translating into a graph like that. All right, but now let's look at momentum. Momentum is denoted with the letter P equals mv. Okay, but now if we represent velocity in terms of acceleration here, we know that this is going to be ma delta t. But now what do we know? This is constant, the mass is also constant, so we've got a constant basically here. Right. So what does that tell us? It tells us that the momentum time graph, because this is a constant, it means momentum is directly proportional to time. So answer becomes D. Okay, there is no inverse proportion, there's no exponential relationship, it's not essentially constant. Okay, so that is the story. So please understand these things and make sure you know how to relate things here, because here we can tell that momentum is directly proportional to time. Having ma as a constant, it becomes the gradient, isn't it? So that is the story that you need to capture, and we move on. And maybe we can just push this one a bit. Ooh. Yes, I don't know why it likes to do what it does. Oh, this thing is about to drive me crazy. Anyway, so we can say here, therefore, the change in velocity, I'm just wasting time now, it's directly proportional to the change in time when acceleration is constant. So I just wanted you to be able to appreciate these graphs. Nice and easy. Okay, let's quickly finish. The impulse is equal to the final momentum of a body? No. Initial momentum? No. Change in momentum? Yes, because the impulse equation is F delta T equals delta P. So that is the story. The rate of change of momentum is just the force, okay? So the answer here is C. So knowing this formula makes your life a lot easier. Moving quickly, which one of the following combinations correctly indicates the strongest intermolecular forces found in ethanol, okay, and ethanoic acid okay? And ethyl ethanoate. All right, so now we know that this is an alcohol. We know that this is a carboxylic acid, and we know that this is an ester. Okay, now we know that ethanol, which is alcohols, and carboxylic acids, they have the stronger dipole forces that are called hydrogen bonding, which is not true bonding itself, but because it's so strong, it is almost as strong as a bond. So we know that this is hydrogen bonding, and this one is not necessarily called a dipole force. It's a special kind of a dipole force, but called a hydrogen bonding. Ethanoic acid, we know that we're talking about this, not necessarily called a dipole force. But in ethyl ethanoate, it's just a standard dipole. So it does not contain hydrogen bonding. So which one ticks the boxes is D. Okay? No, you're lying here when D is not ticking the boxes, but B. Yo. Okay, let's do the last question. The following is the structural formula of an organic molecule. Okay. Now, which one of the following is the correct IUPAC name? So now we're looking for the name. Now the key is to find the longest chain. So if we're starting here, we're going to say if we're starting on this carbon, it's going to be 1, 2, 3, 4 on the straight chain. And if we're starting on this carbon, it's going to be 1, 2, 3, 4. So whether we're taking it as a bent one or the straight one, we have 4 carbons. So once the straight chain works, I always just take it for convenience. All right. The next thing is, how do we number? First of all, what is this? These are all single bonds, so it's a saturated compound. Okay. 2, we have this bromide ion, and we've got this chloride ion here. No. Okay. So now these ones are halides. Okay. So this makes it a haloalkane. Now, if it is a haloalkane, either one of these two we can regard as a functional group, so to speak. Okay? Now, we always prioritize the functional group. So we want the shortest distance to the functional group. Whether you're choosing the bromide ion as the functional group or the chloride ion as the functional group, the idea is that you cannot name this structure from this left end. We have to name it from the right end because it is the shortest distance to either of the two halides. Okay, so this becomes now carbon 1, 2, 3, 4. And then of course we've got this methyl group here. No, not how I want it. So we've got that methyl group. All right, now this means we've got 1 bromo, B comes before C, right? 1 bromo, 2 chloro, 3 methyl butane, because there's 4 carbons. So this is 1 bromo, 2 chloro, 3 methyl butane. So that's the correct one. So that's good. That's the answer. But why are the others incorrect? Let's look at this one. It says 4 bromo. So it means we started from this end here, the left end. It's 1, 2, 3, 4. And then 3 chloro. And then 2 methyl butane. So technically this is what I would call, it's jazz if you think about it. It's an organized chaos. Okay, so if you think about it, we just did not prioritize anything. We just went about it, but in an organized fashion. So if you listen to jazz music, this is what you're doing here. And We don't do jazz in chemistry. We go with the standards, okay? Anyway, 2-methyl, 3-chloro, 4-bromo. So do you see M doesn't come before B and C? So here, this is total chaos. Okay? And what music is total chaos? Is it rock music? I don't know. But there's just some type of music that are just, chaotic. Total chaos. Total chaos. So here, this is all chaotic. Same story here. It's just a mixture of nonsense here. So here, it doesn't follow any rules. Remember, this is a rule. It's not a guide. Remember, there's a difference between a rule and a guide. A guide is what you would do when you have nothing else to do, but you're not forced to do it. But a rule you cannot do without, okay? So this is a rule. IUPAC is a rule, not a guide. So you can't just chop and change. Anyway, let's move on. So the answer there becomes A. Anyway, 2 blocks of mass is 4 kilograms. Right, and 8 kilograms respectively are connected by light inextensible string. You know already what that means. No weight added by the string, and technically no force is dissipated, meaning the tension stays constant. If they are moving, they're moving at the same unit, okay? That's the thing. So a second light inextensible string attached to block 4 kilogram. Block, wow, I don't know. Attached to the 4 kilogram block runs over a frictionless pulley, okay, meaning the tension here, if we call it T1, it's going to be the same as the tension on the other end of the pulley. A constant horizontal force F pulls the second string as shown in the diagram. The magnitude of tension between the 2 blocks is 120 newtons, so we can see that, not a problem. Ignore the effects of air resistance. So we've got ourselves a closed system. So only gravitational force and this particular force are acting. Okay. Great. So let's sort out this thing. It says state Newton's second law of motion in words. Okay, this is now grade 11 work. So if you fail this one, hang yourself, please. Newton 2 states that a resultant force applied to an object will cause the object to accelerate in the direction of force. Okay, such that the acceleration is directly proportional to the resultant force. And inversely, okay, this one didn't come out right. Okay, inversely proportional to the mass of the object. That's quite a passage, okay? But you have no choice, but you've got to do it, okay? 2.1 says, draw a labeled free body diagram showing all forces acting on the 4 kilogram block, okay? So that's fine. The 4 kilogram block, we know that there's about 3 forces acting on it. It is the applied force acting upward, okay? So we can just say that one is not quite straight up. So we can say this is the applied force. And then we've got the weight, all right, which is going to be definitely smaller than the tension right there, because the tension is 120. So this is going to be now the tension, T2. And then we can say here this is the weight, which is Fg. Okay, easy stuff. But maybe we can just use T for tension here. It's still not a big deal. And then we just say that one is the applied force. Great, easy stuff. 3 marks, 1 mark for each of the 3 forces. Let's move on. 2.2. What is the question? Calculate the magnitude of the force applied on the system when it is accelerating. Okay, great. So what do we do now? Now we have to think about what we're going to do. We need acceleration for us to be able to find that force, isn't it? Yes, so the best thing to do now is to find work on the 8 kilogram block first. So let's say, consider the 8 kg block. So what is going on in there? We know that the 8 kg block, there's 2 forces acting on it. It is the tension and its weight. Okay? Alright, so using Newton's second law, we know that the resultant force equals ma. This implies, so if we're moving upward, we definitely are. The tension is greater than the gravitational force. So we know that the tension minus Fg is going to be equal to ma, right? Which implies that 120 minus 8 into 9,8 equals 8a, right? Therefore, our a is going to be equal to 120 minus 8 into 9,8 divided by 8. Okay, so what is the story there? Let's calculate. So I'm getting 120 minus 8 into 9,8 divided by 8. So I'm getting a 5,20 meters per second squared upward, isn't it? The acceleration is going to be upward because it came out positive. Of course, with these kinds of questions, always choose a direction here. So it's always important. Somewhere you must indicate how you are considering things, okay? Great. But the problem is that do not take, if you're going to say resultant force, for you to correct for this negative, you put a plus and then you put a negative for the gravitational acceleration, or you pull out the negative, then you leave it positive. Ne? So don't get yourself confused. So, and then we say now, what about the 4 kilogram block now? Okay, now there's how many forces acting on it? It is going to have I mean, how you plan your attack is easy. It's totally up to you. Okay, so we're going to have its weight, we're going to have tension, and then we're going to have the applied force. All right, so what do we know here? We know that Newton's second law tells us that the resultant force, F res, it's not res, it's F sub res equals ma, which implies what? That force is bigger, so it's the applied force minus the sum of these two, tension plus Fg. This one didn't come out all right. Okay, equals ma, which implies now that the applied force is going to be equal to ma plus tension plus Fg. Therefore, the applied force is going to be 8 into, sorry, not 8 this time, this is the 4 kilogram block, into 9, oh, don't do it. The acceleration we got is 5,20, right, plus the tension is 120, plus 8 into 9,8. I keep writing 8. Stop this thing. Okay, so let's do the calculation. It's pretty easy now. It's 4 into 5,20 plus 120 plus 4 into 9,8. So I'm getting 180. Not kgs, but newtons, Upward. Of course, they just said magnitude, so you can just leave the rest of the complexities. Anyway, so this is how you do it. So once you see a 4 marks, you know that you're going to do it in 2 stages, but this one is even more. So again, identifying the law to use and essentially correct substitution, and that intermediate answer is important. But here what matters now is the substitution and the answer. The rest is a means to an end. Okay, easy 5 marks there. Let's move on. Question 3 says 2 metal balls A and B are rolling along a horizontal straight line towards each other in a closed system. All right, closed system. What do we know about closed system? We know that, well, momentum definitely will be conserved, but what about kinetic energy? It may or may not be conserved because energy can freely escape or enter a closed system, right? Right, but no other forces are allowed. Thank you. Now we're saying here ball A of mass 0.75 kg, rolling at a speed of 4 meters per second. Okay, not a problem. And then ball B of mass 1.25 collides head on with ball A at a speed of 3 meters per second. Okay, now after collision, ball A rolls in the direction opposite to its initial direction at a speed of 2.5 meters per second. Again, with momentum, you choose direction. So we'll choose eastwards as positive, okay, because we can see this is moving eastwards, this is moving westwards. All right, calculate the change in momentum experienced by ball A. Okay, great. 3.1. So we can say now the change in momentum for A is going to be equal to mass into the final velocity minus initial velocity, isn't it? Which is going to be equal to 0.75 into the final velocity. Remember, it's negative, so it's 2.5 minus the initial, which was 4. Is it so? Yes. Now let's do the calculation quickly. So we've got 0.75 into minus 2.5 minus 4. So we're getting here a minus 4.875. Remember, this is an intermediate step. So, this is the final answer. So we can do 2, we can do 3, we can do more, but no less than 2, essentially. So here, just to keep to the standards, this is going to be 88 to 2 decimal places, which we can interpret as 4.88 kilogram times meter per second. Now, remember, in the opposite direction. Remember, this ball was moving east. So you could easily say west. Okay? Or you can use an arrow directed like that, because momentum is a vector, and here we're not told exactly what to do. So you've got 2 options here. You can say in the western direction or opposite direction, or you can just use an arrow. The last time I checked, an arrow was accepted. I don't know if it is still accepted. So that is the story, guys. So you're getting a mark for the formula, substitution, the answer, plus direction, because it was necessary. So that's why it's 4 marks. 3.2 says, use the change in momentum of ball A. This one should be A, I suppose. You can't say ball B to calculate the velocity of B. Nah. So we can say here 3.2. We know that the change in momentum of B is going to be equal to m to final velocity, initial velocity. Okay, that's fine. And then what are we going to say now? We're going to say, but we know that the change in momentum of ball B is going to be equal to the change in momentum of ball A. Now, what is the story here? We know that this is an isolated system. Momentum yo kanti tenda palaga bingo. Momentum is conserved in a closed system. So always know these things. Therefore, this tells us we're going to have 4.88. Remember, this one was in the western direction. This one is going to be in the eastern direction. Okay, they will change in the different directions because it stopped, isn't it? So this implies what? That now 4.88, we're going to substitute it as positive because it's eastwards. And then it's going to be the mass of that object, which is 1.25, into the final velocity, which is what we want, minus the initial velocity was westwards, so it's minus 3. Okay, so that's what we do, which also implies, in fact, we can make our conclusion. We don't want to make it too long. So we can say, therefore, the final velocity is going to be this guy, 4.88. I don't know why now my writing is fading. Divide by, and we're going to divide by 1.25 first, and then this becomes positive. When you transpose it, it becomes negative. Nah. So you know what to do. So let's do this one finally. So we've got 4.88 divided by 1.25 gives us that. We subtract 3 from it. We're getting a 0.9 meters per second, and this one came out positive. So this one is definitely going to be in that direction. Let me see, what is the story here? What was the question here? Yeah. We wanted the velocity of B after the collision, so that's cool. We've done it. So it is in the opposite direction, or eastwards. You can write east. You can write opposite its initial, because here they said change in momentum again, so direction is important. So instead of just the arrow, you can use east because it was initially traveling west, or say opposite direction to its initial motion. It's already okay, so you've got options here. Now this is fine, but I think what matters here is this statement right here, right? For me it matters. And then we can say correct substitution, and then the correct answer. How many marks were there? 4, because there is an issue of direction there. Okay, great. Is there any more questions? It says now, what is the net change of momentum for the whole system? Remember, from the law of conservation of linear momentum, the sum of momentum before is equal to the sum of momentum after, right? So meaning the change should be 0 because they will cancel out, isn't it? So 3.3, just going to say 0, or you can just write 0 like that. Great stuff. That's it. Then let's see what is the next story. Calculate the magnitude of the average force that ball A and ball B exert on each other during collision if the two balls were in contact for 0.2 seconds. That's easy. So we know that the impulse equation is going to be, I like to write A, I don't know why. F delta T is equal to change in momentum. Then we're going to use ball A. In fact, let's just do this one. Let's just say consider ball A. You guys in metric, you need to be more organized. Please don't adopt any hooligan, should I say hooliganism. So we know that this implies that F is going to be equal to delta T, delta P over delta T. I hate those deltas also. But anyway, what can I do? So we know that this one was minus 4.88 divided by, now the time is 0.2. So let's get the answer. Nice and easy. 4.88 divided by 0.2. So this is 24.40 newtons. And then we can just say this is 24.40 newtons on each other. Okay, it's easy because now the direction is interchanging according to Newton's third law. It can be west, it can be right, so we're not going to worry about it. If we said they are doing it on each other, we are sorted. Great stuff. So here, formula, substitution, answer. Thankfully, they just wanted the magnitude. So that's it. So the next question says, is the collision elastic or inelastic? Explain the answer by means of calculations. So this is easy. So 3.5, we can say now the sum, oh no, let's not write too much English. The sum of EK before is going to be equal to half into 0.75. Here you can just jump in. You don't need to be writing too much. Into the first one was 4, right? Yes. squared plus this one is half into 1,25 into minus 3. Remember that one was moving at that one. So let's see what is the story. 0,5 into 0,75 into 4 squared. Okay, plus 0,5 into 1,25 into minus 3 squared. So the answer here is 11,625 joules. Okay, it's a scalar quantity, and then we can say the sum of EK after is going to be a half into 0,75 into, we saw that this is minus 2,5 squared, plus a half into 1,25 into this one, we got 0,9 squared. Let's see what is the story. 0,5 into 0,75 into minus 2,5 squared plus 0,5 into 1,25 into 0,9 squared. So my answer here is 2,85 joules, and we can see here which is not equal to the sum of EK before collision. And what does that conclude? We can therefore say the collision is inelastic as the sum of the kinetic energy is not conserved. Okay, great. So that's it. So you're going to get your marks here, and then you're going to get your marks there. I'm not too sure how these 5 marks come about, but it's okay. Easy. Now let's move on to this question quickly. Question 4 says the graph below shows the velocity time graph of the ball that is dropped. So if it is dropped, what does that mean? The initial velocity is 0 and bounces. Ignore air resistance. Okay, we already know what those things imply. Now we can see that initially it was at 0 and then it increased. So you can see that in this graph, downward was regarded as positive. So always be sharp on the directions and what was chosen. So this ball will drop from this height, drop down to the ground and hit the ground with the velocity of 8 meters per second down. So this is ground. My ground doesn't look right. Okay, and then it bounced off the ground at a velocity of 4 meters per second, and then it reached the maximum height D. So D is the maximum height. After the first bounce. Okay, remember that. Okay, great stuff. Now that is what we can say, and then of course we know that the area underneath the graph will tell us the displacement, okay, or the position, as well as this one. It will tell us about exactly how high is that maximum height from the ground. Okay, easy stuff. So let's move on. So the two learners argue about the ball in the above scenario. One learner says the ball is a projectile. Well, when I'm mega mona 4 seats, yeah, that one is lying. Definitely it's not a projectile. Why? Because it dropped, so we didn't give the initial velocity. And while the other one says it is not, and this one is definitely true because it is not. Why? There was no initial velocity given before it undergoes free fall. Yes. And then now let's define what a projectile is quickly. So this one is 4,1. There's too many things here now. 4,1,1. The projectile is defined as an object that is given an initial velocity and undergoes motion influenced by the gravitational force only. Okay, great stuff. So it is undergoing free fall, but it gets an initial velocity. That is the most important. So 4.1.2. What do you want? It says now describe the motion of the ball between A and B. All right, between A and B, you can see that this projectile essentially just dropped from an initial velocity of 0, and it accelerates due to gravity to attain a velocity of 8 meters per second as it hits the ground. That's it. So let's just go on. So we can say the ball is accelerated. Come on now. Accelerated from rest due to gravity until it reaches the ground with a velocity of 8 meters per second downward at point B. Okay, I don't know, something is not happening the way I want it. At point B. So the ball is accelerated from rest due to gravity until it reaches the ground with a velocity of 8 meters per second at point B. Okay, maybe we can say from rest at point A. Okay, it is accelerated from rest at point A due to gravity until it reaches the ground with a velocity of 8 meters per second downward at point B. Sounds complete to me. Now 4.1.3. Okay, we've got Roman figure 1 there. It says determine, from the graph by the way, determine the direction in which the ball is moving between point C and D. This one is moving upward, isn't it? Because it reaches a maximum height when it is getting the velocity of 0. So between C and D, it's moving upward. Okay? Because we saw that upward was negative here. Now, the number of times the ball bounces, it only bounced once because it is just at the maximum height here. So we don't see any more bounces. So we can just say once. from the graph, of course, but it may have continued to bounce as many times as it wanted. Okay, now here it says the time at which the ball is at its maximum height. Remember, maximum height is the highest position this ball has reached. So for me, it will be at 0 because that is the highest height this ball is at in the system. So we can say 0 seconds. That is the highest. Okay. Now explain why the velocity at C is less than at B. Okay. We can already tell here that the velocity with which it leaves the ground is less than the velocity with which it arrived to the ground. So what happened? There was an impulse, right? Or an impact that happened. So there was a sound energy, as well as the ball got deformed to some extent, depending on its pliability. So there's deformational energy and kinetic energy. Sorry, kinetic energy there, its maximum, isn't it? Therefore, some of it gets converted to sound and the deformational energy. Hence, the kinetic energy that is left behind is much less, as we can see from that velocity. So we can just simply say, for 4.1.4, we can say the ball, okay, we can just say the kinetic energy of the ball is, so you can say in part, okay, in part, not all of it, is in part converted to sound energy. Why do you write like this, man? Come on. Converted to sound energy and deformational energy, if there's such a word. But in any case, what can we explain it by? It deforms, therefore we'll say deformational energy. So we can say, hence, the kinetic energy was not conserved, resulting to a lesser velocity as the ball, I'm singing. Okay, as the ball leaves the ground. But of course, guys, you want to be as complete as possible. There's no joy in you guys cutting the corners, okay? This is brief, it's not too long. So kinetic energy of the ball is in part converted to sound energy and deformational energy. So these are the two energies that are possible there, okay? Hence, the kinetic energy of the system was not conserved, resulting in a lesser velocity as the ball leaves the ground. I think this is complete. Okay, guys, let's move on. We have got a second part here. Now, we're told a ball is thrown vertically upwards, okay, from a balcony of a tall building with a velocity of 12 meters per second, okay? So this one becomes a projectile, okay? On its way up, the ball passes a window which has a height of 1 meter, and we can see that on the diagram. Now the ball is the balcony is 4 meters above the ground. So this is meaning to tell us that this height over there is 4 meters. Okay, not a problem. The velocity of the ball at the bottom of the window is 8 meters per second. So this means the ball here is doing 8 meters per second upward. Okay, while the ball here is doing 12 meters per second upward. Great stuff. And then that is 8.1, not just 8. Okay, great. So what happens to this ball? Of course, it's going to go reach some maximum height, come back to the position at which it was released. All right, so if it is 12, there's going to be minus 12 meters per second down. Okay, maybe let's just say 12 down instead of minus 12 down. Okay, and then it may continue to reach the ground depending on whether someone catches it or not. All right, so that is the trajectory we need to consider. So we told you define free fall, easy stuff. Ach doch. 4.2.1. Okay, what is a free fall? So this is motion of an object, right, under the influence of gravitational force only. Okay, that is easy, 2 marks. So 4.2.2, what is the story? Now we've got Roman figures there too. Okay, Roman figure 1, it says calculate the time taken for the ball to reach its maximum height. Okay, easy. We know that at the top the velocity becomes 0 meters per second. Okay, so we can use this one. So v final equals the initial velocity plus g delta t, because this is nonetheless a free fall. Okay, which implies that 0 is equal to 12 plus this one is minus 9,8. Of course, you have to choose a direction. I always forget to mention that. So here I always find it easy for these kinds of projectiles to choose upward as positive. It makes a lot of sense for me. Okay, so therefore our delta t is going to be minus 12 divided by minus 9,8. Okay, let's move, guys. Minus 12 divided by minus 9,8. This is 0,2. This is 1,2. This is actually 3, you know. Yeah, this is 3 seconds to 2 decimal places. Anyhow, this is easy. Formula, substitution, answer. Easy, 3 marks normally. Yes, definitely. So we want the maximum height reached by the ball. Okay, so we know that we can use this formula, that v, the final velocity squared, is equal to the initial velocity squared plus 2g delta y. Right, this implies that 0 squared equals 12 squared plus 2 into minus 9,8 delta y. Therefore delta y is going to be minus 12 squared divided by 2 into minus 9,8. Okay, let's see. 144 divided by 2 into 9,8 is basically 7, 3. So I can do to 2 decimal places already, 5 meters here. All right, because I know the next step is simple. You can say therefore maximum height is going to be equal to 4 plus 7,35, which is going to be 11,35 meters. 11,35 meters. Of course, this one is above the ground, so you don't need to explain too much. It's a scalar quantity. So the maximum height, remember, you will always include this guy. Don't forget it. Although we calculated from here up there, we need to include that because that is the highest height. Okay, so never forget to add this one. So formula, substitution, this answer over there. But now we're supposed to get what? 3 marks. Okay, so remember, you're not forced to give a mark there. So yeah, this is another question here. What am I doing here? This is where we're not forced to get a mark there. We can just mark the substitution, that intermediate answer, and the final answer. Okay, great stuff. So is there anything more? Now it says the time the ball takes to reach the top of the window. The time it takes the ball to reach the top of the window. Okay, so now I'm trying to think. Now, what are we talking about here? Are we talking about the time from its launch to the top of the window, or from the bottom of the window to the top of the window? This question is a little bit vague for me, because when it says the time it takes, for me, I will think of this portion too. I don't know if I should forget that portion, because that portion is important, so that I can calculate the time it takes from this ball to be launched until it reaches the top of that window. So for me, it sounds like that, because they didn't specify as to when is this ball doing what it's doing. So for me, I will think about it that way. So to plan this attack here, we're going to run out of space here. When excellent, kuyakuthanda kundisokolisa. Doch. Hayi ke sondihlanyisa pen. Theni ngoku yaba off center. Le pen yenzani ngo? Yabona ke ngoku andazi sekwenzeka ntoni. Inaba sekukudinwa ke bantakwethu. Jonga nje bandenzani. Why am I choking on this thing now? Sure. Heaven. Anyway, so what do we need here, guys? We need to find the time it took this ball from where we released it to where it got to that velocity of 8.1 meters per second, right? So we can use this one. So we can say from release, from projecting, okay, we can just say from balcony to bottom of window. Okay, so always indicate some time frames, because when questions are vague like this, your planning will save you from being classified as crazy. Anyway, we know that final velocity is equal to initial velocity plus g delta t. This implies that we've got 8.1 equals 12 plus minus 9,8 times delta t. Therefore, delta t here is going to be 8,1 minus 12 divided by minus 9,8. Okay, maybe let's save a bit of space here by doing our answer over there. Although I don't like to do equal signs side by side. Okay, let's not kill my technique. You know, you got to protect your rep. So 8.1 minus 12 divided by minus 9,8. So here I'm getting, when 8,1 minus 12 divided by 9,8. So I'm getting here an answer of 0,4 0,4 this is not the answer, so I can't really do what I'm doing. So let's just 3, 9, 8 seconds. Okay, so for me, I'm looking at this portion here. This ball moved from the balcony to the bottom of that window over this period of time. Okay, that's the one. And then we can say now from bottom of window to top of window. Okay, to top of window, we know that we can use here delta y equals the initial velocity times delta t. I'm trying to think, do I really need this thing? Yeah, it will save me a lot of problems. Plus half g delta t squared. And then this implies that 1, because this is 1 meter, equals the initial velocity there is 8,1. Okay, let's just not write too much. Delta t plus, now we've got 0,5 into minus 9,8 delta t squared. This implies, now we're going to get a quadratic, right? So this one is going to be minus 4,9. When we transpose it, it's going to be 4,9 delta t squared minus 8,1 delta t plus 1. So I'm already solving and transposing things so that I don't waste time. Now you can see here it's going to be difficult. So this implies that delta t is going to be minus into minus 8,1. Okay, plus or minus the square root, minus 8,1 squared, minus 4 into 4,9 into 1. Alright, so quadratic formula cannot be forgotten. So this is going to be 2 into 4,9. Alright, so let's see what is the story then. So we've got here minus into minus 8,1 plus the square root of minus 8,1 squared minus 4 into 4,9 into 1 divided by 2 into 4,9. I'm getting here a 1 comma 519 seconds, or delta t is equal to, now let's put the negative and see if it does the things that can be done. Hey, oh, this one is giving us a 0.134 seconds. Now these are both positive, so which one do we choose? Bafwat, because now we've got to choose. Now we're in trouble, are we not? Okay, let's have a look. First of all, we need to find out what is that height from the balcony to the, we need to know, because for the speed to have dropped from 8 to 12, we saw that it took how much time to finish off that height. We saw that it took 0.39 seconds. Now we've got to work out something so that we can be convinced of which time is correct. So let's do it. Now we can just say what happened here. We know that we're talking about balcony to window, bottom of window. So we want to know the time. So we know that it's V equals, not time, and we already calculated time. So we want the displacement. So it's going to be V squared. Vf squared is equal to Vi squared plus 2 G delta Y, right? So this is going to be already 8,1 squared equals 12 squared plus 2 into minus 9,8 into 1. No. What am I doing? Delta y. Therefore, our delta y here is going to be 8,1 squared minus 12 squared divide by 2 into minus 9,8. Let's see what that height is. So we've got 8,1 squared, 8,1 squared minus 12 squared divide by 2 into minus 9,8. So I'm getting a 4,0 meters. So look at that. So we traveled a distance of 4 meters. This is 4 meters right there, this one. So we've traveled 4 meters in 0, what is that? In 0,4 seconds, roughly. So basically, it means the answer should be this one, because we can't travel 1 meters over a longer time than we take for 4 meters. So this becomes the time that we want. Okay, so that time we can say, therefore, the total time is going to be the initial time, which is 0,398 plus 0,134. So let's see what we get in there. So this is 0,398 plus 0,134. So now this one is basically 0,53 seconds. Okay, so that is the time it takes to move from the balcony to the top of the window. So this question is crazy. I'm not sure, maybe they missed to say something here. The time the ball takes to reach the top of the window. I do believe that if it is not specified that we're doing the time from the bottom of the window, obviously we have to consider this 2 times. So how many marks are we scoring there? 4 marks. Okay, easy. So let's see, what do we do here? We can just simply say substitution and answer is what matters now. And then here we can just, so much work. Maybe let's do this one like that. No. This one needs more marks. We can say here substitution and the answer, and then the final answer there. So that's how I see this question can be answered, because it was not quite elaborate as to from what time frame, or at least from what position to what position. Now I told you, draw a velocity versus time graph for the motion of the ball from the moment it is thrown upwards until it comes back to the position from which it was thrown. Great. And then use the point from which the ball was thrown as reference. It's really not a big deal when we're doing a velocity time graph. Clearly indicate the following: the velocity with which the ball was thrown upwards, time taken to reach maximum height, the velocity with which it arrives on the ground. No, this one should be from the same position. Okay, because we were told that it is the position from which it was thrown, not the ground. So they didn't phrase this one correctly. Anyway, I don't have space, so I'm just going to attempt to draw the graph right here. All right. That doesn't look right. Okay, looks a bit better. So we know that we're going to have 12, and of course at the bottom it should be, when it reaches the same height, it's going to be 12, but on the negative. This is going to be 0, and then this is going to be time in seconds. This is going to be velocity in meters per second. And then of course, maybe let's not write here this one. Okay, so we can just say this is the velocity time graph of the ball. So always, guys, have a topic or a heading, so to speak, and then label the axis properly and indicate these ones. So we know that the time it took to reach the maximum height is going to be, we calculated it to be what, 1,23 seconds. And then by the time it reaches this level, it's going to be double that time, isn't it? So this is just going to be time symmetry story here. 1,23 times 2. This is going to be 2,46 seconds. And then we know that we just need to do something like so, so that our work is nice and easy. And then we can draw a graph and say this graph will do stuff like that. All right, so there it is. So we are sorted. So we can then sort up some loose ends. So that is the story right there. So we can make this 1,23, and then this time is 2,46, okay, which is double the time it took to reach maximum height. So this is how it looks, guys. It's very simple, no need to panic here. But of course, if they've made this error, so whatever you did, you probably are going to be awarded marks. Let's go on to organic chemistry. Yani, I'm feeling tired already. Okay, question 5 says A to F in the table below represents 6 organic compounds. We've got 2,2 we've got 2,2,5 trimethyl hexane, hex 3-ine. So this is an alkyne. Don't want to worry about it, but it is branched. Okay, and then this one is CH3, CH2. So once you see this guy multiplied multiple times, it belongs in the same chain, so in the chain length. It's not a side branch. So this is 1, 2, 3, 4, 5. So this is basically pentane, so it's an alkane. Okay, pentane. And then we look at this one. Once we see this friend here, not the way I want it. Okay, once we see that, we know that that is a carbonyl group at the end of the chain. So this is an aldehyde. Okay, and then we look at this one. We can see here that there is this guy right here. That is the functional group. Again, what is that? COOH, it's carboxylic acids. Okay, don't worry about naming it. You may not even be asked the question. Again, here with single bonds throughout. So this is a branched alkane. Okay, it's just branched. Okay, maybe that one is not coming out right. Okay, great. And then we're looking at this one. The double bond tells us we're looking at an alkene. Again, it is branched. Okay, good. So we know what we're dealing with, so we can just move on and try to answer the questions. Write down the letters that represent 2 organic compounds that are isomers of each other. Okay, so now let's have a look here. Yeah, we don't really have functional types, so to speak, but if you're looking at this one, 1, 2, 3, 4, 5 carbons, and it's all single bonds, and that is 5 carbons. So this is basically 2,2 dimethyl propane and pentane. Those are chain isomers. Yes, so 5.1. So 5.1.1, we've got B and E. 5.1.2 says type of isomers. We've already identified that these are going to be chain because they belong to the same homologous series. So these ones are chain isomers. Okay, great stuff. 5.1.3, what do they want? The general formula of the homologous series. So now general formula to which D belongs. What is that? Carboxylic acids. Okay, easy stuff. So this one is basically CN H2N plus 1. COOH, right? Right. If you forget this one, take the simplest and say, for example, think of methanoic acid. It is something like that, right? Because remember, carboxylic acids, their functional group is sort of like the hydrophobic end, and then this carbonate ion. In fact, it's not really a carbonate ion, but it's what? I don't know what we call this ion now because it has a hydrogen. Yeah, doch, whatever. Let's leave it for whatever is going on. So we've got something like this, but now do you see here we don't have the sky, so this means it's 0. So we're going to have C0 H0 plus 1, so there's going to be 1H plus this one, so it matches methanoic acid. Okay, great stuff. And then you can take any other form and see if it balances out. Take, for example, ethanoic acid, which is acetic acid. Look at that. So we've got CN, that is 1, so C1 plus 2 is going to be H2 plus 1, 3. So it's going to be H3. So do you see that? CH3, right? No, wait. C1 is going to be 2 times 1 is 1. No, 2 times 1 is 2. God, what am I saying now? Yeah, this is 1 times 1. It's going to be 2, right? Right. 2 plus 1 is 3, so that is the CH3 right there, isn't it? And then COOH. So it matches that formula. So sometimes when you forget, you just test things and see if they are doing the things that must be done. But some things are going to be technical, so it's always advisable during practice to test all the waters, because in the exam it's not possible. You will feel like you are dying there. But if you already tested the waters long before the exam, I can tell you can even test them waters in the exam, because your confidence will be sky high. But be careful though. Overconfidence will kill you. But it won't kill you the same way as it would kill someone who is shaking or someone who doesn't know what they're supposed to know. Anyway, let's move on. This is all textbook work, guys, so you need to know all the general formulae. But because it's so easy to forget, you can work them out. You can always work them out. But you need to do that already when you're practicing so that you don't make mistakes. A lot of things have a lot of coincidences. Let's do this one. Name of the functional group of compound C. Now, compound C is an aldehyde. We know that that is a carbonyl group, isn't it? Yes. So let's see here. This is 5.1.4, isn't it? So we know that this is the carbonyl group, also known as the formyl. So you don't write both, write one. So you can either write formyl group or carbonyl group, because what is it? If you're looking at it, if you see C double bonded to oxygen, that's a carbonyl group. Once you have a hydrogen in there, it already tells you have an aldehyde. But if there was another carbon, we would know that we're looking at a ketone. So it's just a different position of our carbonyl group. So, but for the sake of, making a clear difference between the two, you may want to gravitate to that, but it's not really stiff. If you said carbonyl group, no one is going to mark you wrong. If they do, bring them to me. I will handle them. So 5.2, write down the IUPAC name of compound B. Now, that's easy, Papa. What are you doing? Compound B, that's just pentane. Yeah, when? Okay, it's just 1 mark to show indeed that this is weak. Can't be asking matriculants such easy questions in an exam. Come on, guys. Are you donating marks here? Compound B. man, what am I doing now? Compound F. Okay, yeah, now you're talking. This is something. Now again, we want the longest chain. So what is it? Let's look at the straight one. 1, 2, 3, 4, 5, 6. Okay, so we've got 6 carbons on the long chain. Let's take a branch. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. So the longest chain is 6 carbons. So when it works, I always choose the straight chain to simplify my life. So now what are we going to do? We prioritize the double bond. Now where's this double bond? If we're coming from the end, the left end, it's 1, 2, 3, it's on carbon 3. If we're coming from the right end, it's 1, 2, 3, so it's on carbon 3. So this one doesn't become the priority anymore. But now what takes precedence is the side branches. So we've got these 2 methyl groups right here. So that methyl group and this one. So these methyl groups right there. Now they are taking precedence because the functional group is basically symmetrical on either end. And now these ones, we need the shortest distance to as many side branches as possible. So this becomes carbon 1, 2, 3, 4, 5, 6. So basically this becomes now 2,2 dimethyl. So we've got 2,2 dimethyl. Now the longest chain is a hexane, right? It's a hex. Now we have a double bond on carbon 3, so it's hex 3 in because it's a double bond, so this is an alkene. Easy stuff. So you get a mark for this, the position of the double bond, and it should be 2 marks. They're giving 3 marks. Okay, maybe the parent, the longest chain, is a hex something. Great stuff. So that is how you do it, nice and easy. So now it says write down the structural formula of compound A. Now compound A, the longest chain is a hexane, so we're going to start with that one. Okay, this is 5.3. So we're going to start 1, 2, 3, 4, 5, 6. So where's the double bond? It's on the 3rd carbon. So let's just choose left to right. 1, 2, 3. So here we've got a triple bond right there. Okay, because it's an ine, so alkynes have a triple bond. Great. So now we're going to do 3 methyl groups, 2 on carbon 2 and 1 on carbon 5. Okay, 1, 2. So it's 1, 2, 3, 4, 5. So now we sort our thing. So this one is 1, 2, 3. So it's 1, 2, 3, 4, 1, 2, 3, 4. Doch. Okay, so that is the story. So I believe we've got it right. So this is 2 methyl, sorry, 2,2,3 trimethyl hex 3 ine. Eyivake ngokulento. Ya ngamagama amakhulu lento lena. I-chemistry. Hleka kancinci mfana wami. So I'm sure here the 3 marks are going to tell us about the bond, and then all the side branches in the right position and the long chain or the parent chain. So let's quickly get to question 6, guys, and end this pain. So we told you, question 6, compounds A, B, C shown in the table below are used to investigate a factor which influences the boiling point of organic compounds. Now let's look at these ones. What are they? Once you see something like this, once you see stuff like this at the end of the chain, you know you're dealing with aldehydes. Okay, always remember that. Once you see that CHO at the end, those are aldehydes. Okay, thank you very much. Nicolebu Wangamanda. Define the term boiling point. What is that? Question for grade 10. I mean, you've been defining this from grade 10, isn't it? So the boiling point is defined as a temperature, right, at which the vapor pressure the vapor pressure of a substance is equal to the atmospheric pressure Okay, so that's it. Easy 2 marks from the textbook. Oh guys, I'm tired. Which one of the following compounds, A, B, or C, has the highest boiling point? And explain. Wadlala wena. So we know that, well, the higher the molecular weight or the longer the chain, the higher is the boiling point. So easy stuff. So it's going to be compound C. We can say the longer the chain, the higher. Kuvele kuthini na Nkosi yami? Funa ubhala kahle ke tana, the longer ndavele ndaphinda into efanayo wena. The longer the chain length, the higher is the boiling point. Okay, I don't know if we have to go too far and say because of the increasing strength of intermolecular forces, the higher is the boiling point due to the increasing strength. Andazi ke ngosekwenze njani. Increasing strength of intermolecular forces. I think this is more complete. The longer the chain length, the higher is the boiling point due to the increasing strength of intermolecular forces. I think that one is more complete. 6.3 says, now for this investigation, write down the independent variable. Of course, here this is the chain length. That's what we are changing. 6.3.1. So that is what the boiling point seems to be depending on. So this is the chain length. Okay, Easy, or you can say molecular weight. Okay, or molecular size. It is honestly up to you, but since we spoke about chain length upstairs, it's fair to use it again. 6.3.2. Let's try to finish. The dependent variable now is the boiling point. Because as the chain length increases, the boiling point does the same. Easy stuff. Okay, guys, let's move. 6.4 says write down the names of the two types of the van der Waals forces that occur between the molecules of compound A. Now, compound A, it is what? It's an aldehyde. So it has two van der Waals forces. It is the dipole-dipole forces as well as London forces. So we're going to write it like this. We're going to say weak London forces, and we're not going to say stronger. Is stronger than strong? Okay, anyway, let's not even say anything because they didn't ask us about the strength, so we can say dipole. Okay, dipole forces. Maybe let's not even say weak London forces. They didn't ask about their strength, so we're just going to say London forces and dipole forces. Easy stuff. So 6.5. How will the vapor pressure? Let's see, first of all, we're talking about boiling point, yeah. Now, how will the vapor pressure of 2-methyl propanol compare to that of compound B? Okay, let's look at compound B. This is what? 1, 2, 3, 4. So this is butanol. Okay? Butanol. And essentially, 2-methyl propanol is an isomer of butanol. It's a chain isomer. Okay, so write down higher than, lower than, or equal to. Obviously, the branched chain will have a lower boiling point, meaning a higher vapor pressure. So we're going to say higher than. Okay, now the answer says fully explain. So we can say, what are we going to say now? We can say 2-methyl propanol. Two-methyl propanol is a branched chain aldehyde. Okay, is a branched chain aldehyde. Okay, maybe let's do that. 2-methyl propanol is a branched chain aldehyde, and it will have weaker intermolecular forces than compound B. Okay, than B, therefore less energy is required to separate molecules into a gas. And so hence it will easily form vapor. It will form vapor. Yo, come on, man. Hence it will easily form vapor than B. Okay? And then of course they normally expect you to say something about B. So we can say compound B is a straight chain. Compound. That means stronger intermolecular forces, all right, between molecules. But if you said intermolecular forces, then C, you're comparing, right? Then 2-methyl. Yabafethu andazi sekwenze njani manje, sengivele ngadinwa kakhulu. 2-methyl propanol. Okay, then it will need more energy is required to separate molecules. Hence it will form less vapor than 2-methyl propanol. I think I'm done here. You can even go on and say it will have a higher boiling point and therefore less vapor pressure compared to the other one, but at the end of the day, the story is the story. Okay, so actually you can actually use this one. So what did I say here? Okay, compound B, meaning you can already see here there's 4 points for each. So you can choose either this or that to form your comparison. And as long as you have all of those stories, the stories will hold. Okay, let's move on, guys. So now we've got here, now I told you the boiling points of compounds D and E shown on the table are compared. Okay, so what is that? We've got a carboxylic acid, which is propanoic acid, and then we have here 1, 2, 3, 4. Again, we've got here a butanol, which is a primary alcohol because this OH is at the end of the chain. Okay, so write down the name of the functional group of D. The name of the functional group. So 6.6. So D is basically, this is the carboxylic group. We say the carboxyl group, carboxyl group. Okay, easy. So 6.2. Okay, compound E. Now that is the hydroxyl group. Okay, easy. And then now it says 6.7. The boiling point of compound D, okay, is higher than that of compound E. Fully explain. Okay, all right, okay. Yeah, maniac. Look at this here. We know here that, look, for D, we can just say D has strong. Okay, let's not even say it has. D has 2 sites for hydrogen, for strong hydrogen bonding. For strong hydrogen bonding between its molecules compared to E, which only has 1 site. Okay, because these ones they've got hydrogen bonding, so we can say therefore more energy is required to separate molecules of D than those of E. And what is the other story now? The other story is that therefore D will have a higher boiling point than E. Yawan diniwe nango. Yawan balekabi ngizayibona later of words. So what is important is to mention the type of bonds and the fact that we've got 2 sides there. I think it's important. And then the energy requirement and the correlation with the boiling point. So that is it. Done. Sorry. So you can use compound E in comparison to D. So I'm tired now. So that is it, guys. That's the end. So good luck. I hope you've had a nice review and you're going to at least understand some of the shortcomings on this paper, and they were there, you could see them. But at the same time, it was a very good paper, a very fair paper for matriculants, and I believe you guys must have scored distinctions at least. That is what is important. The rest is not that much important. You want to build a very strong portfolio mark so that you don't have to sweat for a distinction in your finals. So don't take these exams for granted and think you're only going to push in your final. This bad portfolio mark that you're going to be acquiring is going to have a weight on how much you're getting in your final. Even if you score a very good mark, you may end up with some mark around 60, or if you're lucky 70. But what if you want an A+? So you don't want to be sabotaged by carelessness at the beginning of the year. Anyway, guys, that's it. Goodbye for now. I'll see you later.